10 days before the workshop, Ramon emailed me and he said, I have a family emergency, I can't make it. Can you please give my talk? So I said, sure. I mean, he's a friend, he's a colleague, so of course I would do that. So I will give his, disclaimer, I will give his talk as he wanted it, but since I'm also a dynamicist, I may not agree with everything that he says, okay? And this is work that he has done with the usual Morbidelli mafia and so forth, okay? So, if we want to study planets, we have a star, and we basically understand now from the Kepler satellite and from radio velocity and so forth that most stars have planets, okay? So, from that, we have come to understand that more than 15% of the stars have gas giants. And as was discussed earlier today, there seems to be a strong correlation between the formation of gas giants and the metallicity of the star. If the star is very metal poor, you would tend not to see any gas giants. If the star has a lot of metals, we tend to form gas giants. And of the gas giant planets that we have seen so far, about 10% of that more than 15% seem to have gas giants on fairly nicely circular and coplanar orbits, while the far majority of gas giants that we see seem to be in very elliptical orbits, which suggests that there was some dynamical mechanism at play, either recently, ongoing, or in the past, that has excited these orbits. The remaining roughly 85% or less of stars that have planets tend not to have gas giants, and most of these tend to then form a series of these super Earths or mini Neptune systems that are reasonably well packed and compact, with the majority of them situated fairly closely to the star. Of course, there's a selection effect in here, because with transits and with radial velocity, we tend to preferentially target planets that are closer to the star. So we have what he would call solar system-like planetary systems. We then have what Ramon calls angry gas giants. I don't know why. And we have these hot super-Earth systems, which I mentioned a few seconds ago. So the stages of planet formation, if we understand how planets are built, what are the key ingredients and the mechanisms behind that, we have roughly, through the past 30 years of simulations and cosmochemistry and so forth, and all the things that are going in this, we've come to understand that the process works roughly as follows. So we start with grains, right? We have solids and gas in the disk, and we have then grains, dust grains, which then try to coagulate, and depending on what the relative velocity is and the porosity and so forth, the grains either bounce or stick. It's easier to assume if they stick, because that makes the mathematics and the dynamics and so forth a lot easier. And these grains then tend to coagulate into what we call pebbles. And here's a nice picture of pebbles here. And one time a colleague of mine said, astronomers have a different definition of pebbles than geologists and geophysicists, so you have to be careful. Then the pebbles, because they are so strongly coupled to the gas, or not, depending on what their size is, they tend to drift very quickly to the star. So in 1,000 years, all the pebbles have migrated to the star. And that then leads to the regime of pebble accretion, which is a new way of forming planets. I will not discuss that here. That is an ongoing topic, a heavily ongoing topic of research, but for the moment I will just focus on planetesimal accretion. So the pebbles, eventually they can grow larger through coagulation and sticking and so forth, and they grow into planetesimals. And then the planetesimals will eventually just smash into each other because they excite each other and they cause the heating of the solid disk to increase. They increase their velocity dispersion, and they go through runaway and oligarchic growth, and eventually they form planetary embryos. These are about the size of the Moon to Mars or the Galilean satellites, approximately. While the gas remains, this is all ongoing. And these planetary embryos, if there is gas around, they tend to migrate under so-called type 1 migration, which is mostly inward migration for planets roughly less massive than about 20, 30, 50 Earth masses, depending on the scale height of the disk. And in some cases, these planetary embryos get lucky if they form very far out, and then if they have enough time, they undergo runaway gas accretion through envelope contraction and so forth, and you can form gas giants such as Jupiter and Saturn, and in sometimes ice giants. And these gaseous planets, they first undergo type 1 migration, and eventually they undergo type 2 migration, in which they open an annulus in the disk, and then they're basically pushed inwards by the disk towards the star. And if there's no more gas, then these gas giants tend to scatter each other sometimes, or most of the time in fact, and then you get dynamical instabilities and you leave with 1 or 2 gas giants on eccentric orbits. And these planetary embryos in some cases can also form terrestrial planets depending on where you form and what time you form and what the scale height of the disk is and so forth. So as you can see, there's a lot of stuff that goes on in here, right? We need to understand dust and pebble formation and coagulation. We need to understand migration. We need to understand planetesimal formation. We need to understand gas envelope accretion. And eventually, you know, some of us can then also focus on how you actually form terrestrial planets without gas accretion, without these envelopes that we see in many Neptunes from planetesimals. So this whole planet formation business is a complete mess, with lots of people working on different things, and we're all trying to patch things together. I need to speed up. So I'm going to tackle 3 subjects. First of all, the inner solar system. So the classical method for the inner solar system is you put down a disk of planetesimals situated between, let's say, 0.5 AU and 5 AU. You have a gas giant here, Jupiter in this case. This is eccentricity, this is semi-major axis. The color coding has to do with the amount of volatiles that you have in the planetesimals. So these red ones are completely devoid. The yellow ones and some volatiles in here, and these have a large amount of volatiles, 50% or something like that. And what you see happens is that these planetesimals then start to excite each other, and they start to accrete, and you have inside-out planet formation. So you form the first planets that form are actually here through the runaway accretion growth and then the coagulation of planetesimals. And you also see that some of these planets are starting to get funny colors that were not in the beginning. So you see that these are actually a kind of like a cyan greenish color, which means that they have accreted both material from the inside of the disk, which is red, and material from the outside of the disk, which is blue. And that then basically kind of accounts for the volatile amount in these planets. The other thing is that you notice that it's inside-out growth. That makes sense because the orbital period scales as a to the 3/2 power, and in a portion of the disk, the orbital period is a lot shorter, so all the processes happen, let's say, 10 to 100 times faster than near Jupiter. Okay, so you have inside-out growth, but notice that the size of the dots is actually representative of the mass of these planets, and we have like we have an Earth and a Venus analog and a Mars analog at 2 AU, except that it is nearly as massive as the Earth analog. And that's a problem because we know Mars is only 10% of the mass of the Earth. So what you can do is you can run, let's say, 10 to the 12 simulations like this, and eventually you end up with a distribution of outcomes which is such as follows. So here we plot the semi-major axis of the final planet and the mass of the final mass of the planets. And the 4 terrestrial planets are basically these black sort of box-like symbols. So Mercury is here at about 0.05 Earth mass, Venus at 0.8, Earth at 1, and Mars at 0.11. And generally, you tend to get this sort of like, you know, semi-Gaussian-like distribution with a peak at about 0.8 or 1 AU, and then it rapidly falls off. But in the region where Mars is situated, so near 1.5 AU, you see that most of the planets actually have a very high mass, right? They're all Earth mass or higher, more massive, which is a problem because Mars is a lot less massive than the Earth. So how do you overcome this problem? Because it generally tells us that the classical model is is no longer valid. It cannot reproduce the solar system as we see it, although some people would disagree. And the solution came in 2009 Excuse me, I have to improvise because I was not able to play all the animations on my laptop, so I have to go along as I see the slides. One of the solutions that was offered by Brad Hansen in 2009, and he said, well, instead of having a disk of planetesimals that extends all the way to Jupiter, why don't we just truncate that disk at 1 AU? So that means there's almost no mass where Mars is situated today. And in fact, if you then run a simulation only focusing with planetesimals or with planetary embryos situated only in this annulus, then you can actually get this kind of final distribution of the masses versus semi-major axis of the planets. And you have a Mercury analog, which is somewhere here. I think the arrow bar means that you can lose Mercury's mantle through a large impact. You have Venus, Earth here, and you have this more or less this kind of parabolic distribution. And look where Mars is situated right now, you have planets which are roughly 1/10 of an Earth mass. So does that mean problem solved? Well, the funny thing is, how do you actually truncate the disk? Because you can say, well, I just truncate the disk and I watch what happens and say, hey, it works. But you then need to, the next step is then to explain a physical mechanism by which you can truncate the disk. And this has led to something called the Grand Tack model, which was published by my colleague Kevin Walsh in 2011, in which we basically use the migration of Jupiter to truncate and sculpture the disk. The mechanism behind the Grand Tack is as follows. You have a Jupiter mass planet which is growing. Eventually, when it is massive enough, it starts to undergo type 1 migration, so it goes in very quickly. Then eventually it slows down because of type 2 migration, which I explained earlier, which is when the planet has opened up an annulus in the disk, so it is the viscosity of the disk that is pushing the planet towards the star. And you can see that Jupiter is basically slowing down, but it's going sunward. Then what you can do is say, well, Saturn, let's assume now that Saturn forms later than Jupiter. So Saturn is growing, growing, growing. Eventually it is going to migrate, and because it is lighter than Jupiter, it undergoes type 1 migration and it will catch up with Jupiter. So it's basically somebody running over there and I'm hurrying up to try to catch that person, and that is what happens with Saturn. As Saturn is migrating towards Jupiter, it is crossing these mean motion resonances, where the period of the orbital period of Saturn is an integer multiple of the period of orbit of Jupiter. And it turns out from hydrodynamical simulations that you tend to catch Saturn in the 3:2 resonance with Jupiter. So Jupiter does 3 orbits for every 2 of Saturn. And then, you know, by pure magic or not, what happens then is that the torques between the pair of planets and the disk are such that you can then reverse the migration of the pair of planets, and they turn around and then they go outwards into the disk. And somebody mentioned this earlier this week, although my memory is failing me. I don't remember who said that, and what is crucial in this, in order to get the outward migration, is that Saturn is about 1/3 of the mass of Jupiter. If Saturn was the same mass of Jupiter, or if the two were reversed, then this wouldn't happen. So there's some fine-tuning involved, but hydrodynamical simulations tend to show that this is a reasonably robust outcome, or not. And here the gas disk roughly dissipates, and you can then park Jupiter and Saturn at about 5 and 7 AU. So what we can then do is say, okay, we can run a simulation of terrestrial planet formation where we put down a disk of planetesimals, like here, this inner disk, and we have an outer disk of more water-rich planetesimals in blue. We put Jupiter at, let's say, 4 or 5 AU or something like that. We have Saturn just outside of it in the 3:1 resonance, and we can then artificially migrate the planets inward and then tack them, migrate them outward, and can we then truncate the disk and then see what happens with terrestrial planet formation. So I'm going to play the animation. You can see that the 2 planets are moving inward, they're scattering all material out of bang, they turn around, and then they go outwards and they're parked at about 5 to 7 AU. I'll play it again. Notice actually that there's a lot of mixing going on between the red and the blue particles. Oh, I didn't want to do that, excuse me. So you see that there's a lot of red material which gets scattered into the outer solar system and a lot of blue material which ends up here in this inner ring. And also notice now that this ring that was actually first extending all the way to here is now cut at about 1 AU. So you have this pileup of density inside of 1 AU, and then you have a much lower density outside of that. So if you then say, okay, that simulation that I showed you was only the first million years or something like that, but once the giant planets stop migrating, you can then continue the simulation and have these planetesimals and planetary embryos scatter and accrete, and voila, if you run 10 to the 12 simulations or 10 to the 23 or whatever number you can manage, then eventually you end up with this kind of parabolic distribution of the masses versus the semi-major axis. And we have a nice small Mars, and that is very similar to the results from Hansen that I showed a couple of slides ago. So generally now there seems to be some sort of, I wouldn't say a consensus or an agreement, but it seems the prevailing thought seems to be that perhaps the Grand Tack is the best way to form the terrestrial planets in our solar system as we see it. Okay? So then I would like to move on to the next topic which Sean wanted to discuss, which is what happens if you're in one of those systems where you have gas giants. So suppose what happened if Jupiter was not tacked by the influence of Saturn, but it just migrated all the way to the star. Can we then still theoretically reproduce or form the terrestrial planets? And that is what he means then by terrestrial planet formation with angry gas giants. So if we look at giant exoplanets, this is the semi-major axis, and this is then eccentricity. We find that there are, of course, these hot Jupiters here, which are mostly circular because of billions of years of tidal interaction with the star. But there are a lot of them which are actually very dynamically excited, which is very different from our solar system because the giant planets have eccentricities of a few percent. And these are tens of percent that we're talking about, so orders of magnitude more. So there must have been something, some dynamical instability which stirred the planets up, and at least one of them got a very high eccentricity. So, you have orbital migration of these planets because of the type 2 migration that I mentioned earlier, when they open an annulus in the disk and then the disk pushes the planet inward. At the same time, you can also have planet-planet scattering going on if you have multiple of these planets which are migrating and they start resonance crossing and so forth. And then eventually what can happen if you have multiple Jupiters, let's say you have 3 Jupiters in the same system, that system could be unstable, and it seems to be that in many cases it is, and you can have planet-planet scattering. So you go from a nice circular system, they start to orbit cross. You eject one planet from the system, usually the lighter one, and the most massive one remains on an eccentric orbit because of angular momentum and energy conservation. So I think this is a simulation where we have a disk of planetesimals situated between, let's say, 0.3 and 4 AU, and I have one of those angry gas giants that is migrating through the disk all the way to the star, and I'm curious to know what happens with the disk of planetesimals. And one thing to show here is that Jupiter, or I'm just going to call this guy Jupiter for the sake of the argument, is doing 2 things. First of all, you get these pileup of material in these mean motion resonances with Jupiter, and he is also scattering material further out. So Jupiter, in this case, is acting like a snow plow. Right? I mean, everybody that has lived in a cold, terrible climate knows these snow plowers which are going on the road and they're pushing all this snow forward like this, and then some of it actually gets thrown to the side and some of it goes to the other side, but he keeps pushing it. That is exactly what Jupiter is doing here. So it acts as a snow plow and it's pushing all this material in. Some of it escapes to the sides, like with the snow plow, and that then gets scattered outward, which is then parked here. And some of it stays inside of the planet. Look at these guys migrating right through the disk, and then some of that material actually that gets pushed inward by Jupiter can then actually form a few terrestrial planets inside of the gas giant. And you end up with a lot of material outside here. I think the next animation is supposed to be a similar one, except that now the migration is a lot more rapid, and this simulation is actually run for a much longer time. So Jupiter basically crashed through the disk. I'll try to see if I can play it again, because that was indeed very, very fast. Let's start here. Jupiter crashes through the disk. You end up with 2 terrestrial planets. Notice that because of these envelopes that Sean has nicely animated, they actually do accrete some volatiles. And you end up with a host of material here that has been scattered outward by the gas giant, and you might actually be able to form some planets here and there if you wait long enough. Notice now that the simulation is actually going even faster than it was in the beginning. And eventually we're going to settle, we have one planet here which is scattering some material, and we end up with a hot and excited disk where planet formation is actually still going on. And we have some material here. We have a mini Neptune planet here, and we have another mini Neptune planet at 1 AU. So in other words, having a gas giant plow through the disk and migrate all the way to the star is not necessarily fatal for terrestrial planet formation, although it does tend to do a lot of damage. So this is an animation of planet-planet scattering, where you see these 2 planets that are interacting with each other, and eventually something should happen. There we go, that's it. So you see now they have an encounter, and then you can see that one of them is ejected from the system, and the other one there's a third one here, and this one is now much closer. This one is being pulled through gravitational interaction with the innermost planet here, and you can see that, well, there the animation stops. I'll run it again. Excuse me. I'll run it again. So you have one planet here, which is going very quickly, and 2 other Jupiter-sized planets which are out there. And they're going round and around, and eventually, because of secular perturbations between the 2, since they start on eccentric orbits, they exchange angular momentum. You have a close encounter between the 2 of them right there, and then one of them gets ejected from the system, and the other one is left on a very eccentric orbit, which is precisely what we see with all the other extraterrestrial, extrasolar giant planets. So supposedly now that we're going to do something that is really, really fun, I'm going to put 3 Jupiters in a system and let them gravitationally interact while trying to also form terrestrial planets inside of those 3 Jupiters. Why not, right? We have nothing better to do. So, off we go. So we have these 3 Jupiters. Guys, notice here that I'm forming the planets very quickly. Again, I have this inside-out growth happening here, and I have a disk of planetesimals here. This behavior here is basically caused by the disk gravitationally interacting with the outermost planet, which is causing this peeling off of the disk is causing these 3 guys to go unstable. Boom, there we go. And we're basically left with these two gas giants scattering each other. One of them is ejected, and I end up with 2 gas giants on very, very eccentric orbits, right? Because this guy is going all the way to an eccentricity of 0.9. This guy is now all the way at an eccentricity of 0.2. Notice the separation, right? They're separated by about 10 AU from each other. That's very, very, very far apart. All the terrestrial planets are completely gone because they have been accreted by this guy because his eccentricity is 0.8, so he's essentially almost grazing the surface of the star. And this planet was then scattered into the disk, and all the material in the disk here is gone. I want to run that again because that was absolutely delightful. So we start with 3 Jupiter-sized planets. You know, there's almost no mass in here, so these are fine. This one is gravitationally interacting with this disk. So there's angular momentum and energy exchange between this planet and that disk. That eventually causes this resonance between these 3 planets to break. He's slowing it down, and eventually there we go. we have these two planets scattering the hell out of each other, with this one going on a very eccentric orbit. One of them is ejected. Now all of these planetesimals here are interacting with this gas giant. That causes the eccentricity of that gas giant to decrease, and eventually they basically are, you have two gas giants on very eccentric orbit. I don't know why it is playing again. I apologize. So again, we are slowing it down, and then there we go. So now these, as I said, these two are interacting. They scatter everything in this disk, and you end up with two planets. This one on a very eccentric orbit, which basically gets rid of all this material inside, and this one is scattering all this material outside, and eventually you're left with an empty system and only two gas giants on eccentric orbits. So, long story short, I think that it is possible for terrestrial planets to survive the interaction with a single gas giant if that single gas giant stays nicely circular and migrates all the way to the star. But if there's multiple gas giants and they go unstable, then all bets are off. Okay? So the last topic that I will talk about, how much time do I have? Sorry, I can't do the last topic then. I'm running out of time. Is hot super-Earths. So we have these compact super-Earth systems, right, that are basically at 10 to 20 or 50 radii or some stellar radii like that. If you try to form them in situ, some people have tried to do that. You can't actually do that. The spoiler says no. And the reason is that, the migration speed of these planets is much shorter than the lifetime of the disk. So any planets that you form close to the star will just migrate to the star, and that will be the end of it. So they must interact strongly with the gaseous disk, and because they migrate, you cannot form these planets in situ. This should be an animation of type 1 migration, which I'll skip. Basically, you have a planet here that then migrates all the way to the inner edge of the disk in something like 10, 20, 50,000 years because of type 1 migration. And this one I will actually play, so if you try to do that, then you have all these planets which are migrating here, and these are the regions of outward migration. So some planets should be able to make it and migrate out to the disk. These guys are all at the inner edge of the disk. Notice that there's more material piling up, so eventually this resonant chain will go unstable, as you saw just now, and you have one guy which is basically dominating, and there we go. That's the end of it. So you have one guy which survived the migration, all these guys went to the inner edge of the disk, eventually went unstable, and you end up with one massive guy here. I have to stop. I can try to do that again. This is with inward migrating embryos, and I think you end up with the same result. You get this resonant chain, and all of these guys are just going to crash into each other eventually because this material is pushing on that resonant chain. There we go, see? And the mechanism behind that is as follows. You basically have something like you form these embryos, they grow, they migrate to the disk, they interact with each other, and you end up with 3 or 4 planets that are not in a resonance. And indeed, these resonant chains tend to break, usually after some time, although some of them do survive. And why don't we have this super-Earth in the solar system? Well, because one of them formed the Jupiter, that then prevents these guys from reaching the inner guys here. And then the prediction is that if you have any super-Earth systems, then you will not have a gas giant in that system. So, solar system has a small Mars problem, which is solved by Grand Tack. The angry gas giants, they can make wet terrestrial planets, but not if you have a multiple of them. And the hot super-Earths do not form in situ. The migration into resonant chains is unstable, and Jupiter planets act as a barrier. Thank you.